Welcome to the first video of your Topic 1 review. We're going to walk through this video by video, lesson by lesson. You may recognize some of these from before. So let's just start off with the types of data and analysis. There's two types of data, qualitative and quantitative. Qualitative is non-numerical information obtained by observations, typically your five senses, smelling, seeing, touching, and those other two. And quantitative is going to be numerical info, all right? Information obtained by measurement, and the IB says that it's always associated with uncertainty. I don't really agree with that. I mean, if you have two apples, that is quantitative data, but you are pretty certain that you have two apples. So, but that's more for your TOK class, right? So now all measurements will have three parts. So that is going to be the quantity, the unit, and the uncertainty. So 9.0 grams plus or minus 0.1, right? You can put the unit after the uncertainty or before. Nobody really cares. Okay, so let's talk about that uncertainty. So let's just remember we reviewed there's two different ways. In an analog one, you will look at the lines and you are going to make sure that you first estimate one digit past the smallest increment. So let's find the smallest increment here. That's going to, we have 20 and 30. So the easiest way to do it is to count the lines, right? And so, but you guys are pretty smart. Smallest increment is 0.1, right? And so we get up to, and so, but we should estimate one more digit past that. That's what I'm saying. Whenever we make our measurement. And now the uncertainty is going to be this number, the smallest graduation, the smallest increment divided by 2. So the uncertainty in this case is going to be plus or minus 0.5. The number of the significant figures displayed should equal the reading taken during the estimated digit. What would be the reading taken in this burette? So let's see. That would be 25. 25 we're sure about. And then let's estimate, let's see, wait. Okay, so I messed that up. So the increment is not 0.1. The increment is 1. Dummy. You guys are probably yelling at the screen. So the smallest, it's going to be plus or minus 0.5. Right. Okay. All right. So the reading would be 25. Point 1, 2, 3, 4, 5, and then we'll estimate 25.3. That's our estimated digit, and we'll do plus or minus 0.5. So that takes care of that little estimation right here, right? It makes a lot more sense. It lets you know how sure you are about this last number. Now, for a digital uncertainty, it's super easy. I won't screw it up this time. You're going to look at the last digit, and so your uncertainty for this one would be 0.01 because it has 2 decimal places. So the reading would be 45.22 plus or minus 0.01 grams. All right? So I did those examples for you. Now let's talk about accuracy and precision. So precision is the closeness of the arrangements. So if I was to use the target right here, and we have our bullseye, if they are close together, either way off the target, right, they are precise, but not accurate. but to be accurate, they need to be on the target. So typically you want something that's both, right? You want something that's close to the true value or what you're looking for, and you also want them close together. So the difference between precision and accuracy is key here. Now, if you get an answer like this, the simple answer to the way to fix that is to move the target. Maybe you need to recalibrate the instrument. Maybe there's just some systematic error that is keeping you away from this. And you need to adjust that systematic error. All right. You should know the difference between repeatable or replicable. We should call that repeatable. And that is if an experimenter is able to replicate their own results. And then reproducible is if other experimenters can do it. Okay, so this is something like peer review. And this is why we try to do that in class. And we see that in our journals as well. That's why all the science that's been coming out recently, you have to make sure you get your sources from peer-reviewed places. Something that's not just repeatable, it is also reproducible. All right. So now let's move on to experimental error. You will have to calculate experimental error a lot, and please try to do it at any type of experiment that you do. Please do your absolute best to do this. Please always do this in your IA as well. They will look for this. This will be your thing in your conclusion. So really be thinking about this. You're going to take your experimental minus your theoretical divided by your theoretical result. Sometimes the difference up here can be negative, so just take the absolute value of that. So a student obtains results of 25 joules. The literature value is 23. So to calculate the experimental error, you do 25 minus 23 divided by the theoretical results, which is going to be 23. That's the literature value. The absolute value of that's okay. It's a positive number anyways. And we will get, you can go ahead and skip forward. And that will give us an 8.7% error. All right. So now this will be helpful whenever you're looking at you're comparing it to your uncertainty, because you can calculate your uncertainty and see how that works. How they compare, see if your uncertainty falls within this value, because that would be good. Now, do not get confused between the percent yield and the percent error. All right, two very different things. The yield is reflecting on how much product was produced, but the error is how the experimental value compares to the actual value. So yield is a little different. You would just do the actual over theoretical. All right. Now, so for random errors and systematic errors, there's those two types. So random errors are errors that you can't get away from, and you will typically have answers that are too high and that are too low. So we run multiple trials. The solution for this always is to run multiple trials. And so when I say multiple, I mean greater than 5, right? So when you plan your IA, plan for running at least 5 trials. That's the way that's so you can get the maximum amount of points. If you get less than 3 trials, you are going to get deducted points. Now, so ways of doing that are, can be environmental. So like fluctuations in temperature, you can be breathing on the balance, something like that. Airflows and currents actually really produce that. Or if you use a beaker instead of a graduated cylinder, you are going to get a large amount of random error. because of the accuracy of the experiment. All right. So now, when it comes to systematic errors, those are the things that you are doing wrong or the experiment is doing wrong that is consistently making it too high or consistently too low. All right. So an instrument error, experiment. There's problems with your experiment or there's something that you are specifically doing. So if I drew a graduated cylinder right here, you'll be asked to quote a reason for this. When we read the graduated cylinder, we always, let's see. Oh, no, that looks weird. That's somebody's eye. That must be his retina. And we always read it from eye level. If you read it top down, you will read a value that's too low. If you read it too low, you will read a value that's too high, right? Okay. So remember that example because that is a classic one for you to quote on the IB exam. So if we take them. All right. So, all right. So if you are measuring a physical quantity 5 times in the same conditions, if there are only random errors, then the measured errors are too close to the true value. Some will be too high, others will be too low. Now, so let's just show you random and systematic. What they look like on a graph. Random, systematic. So when you plan your IAs, try to plan on thinking about looking at a graph, all right? So let's just say our true value is supposed to be this dotted line right here, okay? Now, if I get 5 values that are consistently like that, all right, then that is random error. But systematic error is like this, okay? You have problems with the experiment, okay? Now, when the final uncertainty arising from random errors is calculated, then it can be compared. This can be compared to the experimental error. Now, this is what you should do in your conclusions of your IAs. Now, in your analysis portion of your IA, you're looking at something like this, where you have your graph. This is your sketch of the graph. And bear with me. You can fast forward. I'm going to draw some lines. And you have plotted error bars for each one of these, because you will plot error bars. Now, and then you will probably draw a trend line right there. That's an easy trend line to see. Okay. Now, that's the experimental trend. Then, let's say if you inserted in the true value right here, and the true value falls within your uncertainty, then random error is your main source of error. But if the true value falls within out of your uncertainty, then systematic error is the source of error, okay? So this is how they really want you to break it down and think about it like this. So really try to see what the expectations are before you, while you plan your IA, okay? All right, and then this is the easiest part. Here is your lab equipment list of stuff you should know. You probably already know them, but this is just a review. Check out each one of these things. Make sure you know every little bit. All right. And that's going to be it for this video. Have a great day.